Alright, if you guys could please turn to Unit 10, Circles. A circle is the set of all points in a plane that are equidistant, that means equal distance, from a given point called the center of the circle. So this is a circle. I think all you guys know what a circle is. A circle with center P, actually let me write this down. A circle with center P can be written like this. So if I have a circle and the center is P, you can name it circle P, or you can write out circle instead. This is the little symbol for circle. Okay. A segment whose endpoints are the center and any point on the circle is called a radius. A chord is a segment whose endpoints are on the circle. So any segment that starts and ends on the circle, that's a chord. And a diameter is a special kind of chord that contains the center of the circle, goes through the center. Alright, a secant line, or a secant is a line that intersects a circle in 2 points, and a tangent is a line in the plane of a circle that intersects the circle in exactly 1 point. The place where it intersects the circle is called the point of tangency. Okay? Alright, I want you guys to notice that I boxed the words segment and line. A lot of people confuse, for example, the chord and the secant. Notice that a chord is a segment. It has 2 endpoints on the circle. A secant is a line. It goes all the way through the circle. Okay? So keep in mind which of these definitions are segments and which of these are chords, or which of these are lines. Alright. In a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint. So in this diagram, line M is tangent to circle Q if and only if line M is perpendicular to QP, as shown here. Okay? Also, tangent segments from a common external point are congruent. So, in this case, if segments RS and SR and ST are tangent segments, then this has to be congruent to this. Okay? Alright. A central angle of a circle is an angle whose vertex is on the center of the circle. In this diagram, angle ACB is a central angle of circle C. If angle ACB is less than 180 degrees, as it is in this case, then the points on circle C that lie in the interior of the angle form a minor arc with endpoints A and B. Okay, so because it's less than 180, it's a minor arc. Minor arcs are less than 180. Okay? The points on circle C that do not lie on minor arc AB form a major arc with endpoints A and B. Okay? A major arc is going to be greater than 180. Major arcs are going to have 3 letters. Minor arcs are only going to have 2. And I didn't draw one here, but a semicircle is basically formed by a diameter, and it's exactly 180 degrees. Okay? A semicircle is an arc with the endpoints on the diameter. Okay, the arc addition postulate is a lot like the segment addition postulate and the angle addition postulate. Basically, if you have arc ABC, the measure of arc ABC equals the measure of arcs AB and BC. So if this was, I don't know, 100 degrees and this was 90 degrees, then the whole arc would be 190 degrees, because 100 plus 90 is 190. In the same circle or in congruent circles, 2 minor arcs are congruent if and only if their corresponding arcs are congruent. So in this case, arcs arcs AB and CD are congruent if and only if AB is congruent to CD. Okay? If one chord is a perpendicular bisector of another chord, then the first chord is a diameter. So in this case, if QS is a perpendicular bisector, so it's perpendicular and it cuts the segment in half of TR, then QS is a diameter of the circle. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So if EG is a diameter and EG is perpendicular to DF, then HD is congruent to HF and arc GD is congruent to arc GF. In the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. Okay, so AB is congruent to CD if and only if EF is congruent to EG. Alright. An inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. So for example, this here, angle ADB, that would be an inscribed angle. The arc that lies in the interior of the inscribed angle and has endpoints on the angle is called the intercepted arc of the angle. So in this case, arc AB would be the intercepted arc. There is a theorem called the measure of an inscribed angle, and there should be a theorem here. Here, I'll add it. There we go. The measure of an inscribed angle is 1/2 the measure of the intercepted arc. So for example, let's say this arc was 100 degrees. If the intercepted arc is 100 degrees, then the inscribed angle that opens up into that arc is 50 degrees. So the inscribed angle is going to be half the arc. Or if I said, hey, this inscribed angle is 60 degrees, then the arc has to be 120. So whatever the arc and the angle is always going to be half the intercepted arc. Okay? If two inscribed angles on a circle intercept the same arc, then the angles are congruent, which makes sense. So if this arc was, just pick a number, let's say 80 degrees, then this angle, because it's an inscribed angle, has to be 40 degrees, because it has to be half the arc. If this angle opens up to the same arc, then this one also has to be half the arc. So it also has to be 40 degrees. So if they open up to the same arc, the angles have to be congruent. Okay? If a right triangle is inscribed in a circle, the hypotenuse is the diameter of the circle. Conversely, if one side of an inscribed angle is a diameter of a circle, then the triangle is a right triangle, and the angle opposite the diameter is a right angle. By the way, when I say the triangle is inscribed in the circle, an inscribed polygon has all of its vertices on the circumference of the circle. Okay, so if this triangle is inscribed in the circle, all three of the vertices lie on the circle. This basically says that in order for this angle to be a 90 degrees, AC has to be a diameter. Also, if AC is a diameter, then angle B has to be 90 degrees. Only certain quadrilaterals can be inscribed in a circle. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So, in this case, D, E, F, and G lie on circle C if and only if, whoops, there's a mistake here. Give me just a sec. Erase this whole line. Sorry. Okay. If and only if E plus G equals 180 degrees and D plus F equals 180 degrees. So the opposite angles in the quadrilateral have to be supplementary. Alright. Now, you know that the measure of an inscribed angle is half the measure of its intercepted arc. This is true even if one side of the angle is tangent to the circle. If a tangent and a chord intersect at a point on a circle, then the measure of each angle formed is half the measure of its intersected arc. So, for example, here we've got a tangent line and a chord. Angle 1 is going to be half of this arc, and angle 2 is going to be half of this arc, just as though they were intercepted. Or, I'm sorry, just as though the angles were inscribed. Okay? If two lines intersect a circle, there are three places where the lines can intersect. If you have lines that intersect inside the circle, if two chords intersect inside a circle, then the measure of each angle is 1/2 the sum of the measures of the arcs intercepted by the angle and its vertical angle. So basically, if I wanted to find the measure of angle 1, I can take this arc and average it. So like if this was, I don't know, 50 degrees and this was 30 degrees, these vertical angles here, so angle 1 and its vertical angle, they would be the average of 50 and 30, which is 40. Okay? Same thing with angle 2. Angle 2 would be the average of this arc and this arc. So add them together, divide by 2. If a tangent and a secant, this is a tangent and a secant, or if two tangents or if two secants intersect outside a circle, then the measure of the angle formed is 1/2 the difference between the measures of the intercepted arcs. So basically what you want to think, whether you have two secants, two tangents, or a secant and a tangent, the angle outside the circle is going to equal is going to equal half the outside arc minus the inside arc. So this angle is half this arc minus this arc. This angle is half this arc minus this arc. Alright? Okay. When two chords intersect in the interior of a circle, then each chord is divided into two segments that are called segments of the chord. So like AB is a chord, so AE and EB would be segments of that chord. And same thing with DE and EC. DE and EC would be segments of the chord CD. Okay? If two chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So in this case, this times this equals this times this. Okay. A secant segment is a segment that contains a chord of a circle and has exactly one endpoint outside the circle. So both of these would be secant segments. The part of a secant segment that is outside the circle is called the external segment. And I should probably label that. So in this case, EA would be an external segment, also EC, but I didn't draw a line over here. So the part of the secant that is outside the circle is called an external segment. If two secant segments share the same endpoint outside the circle, then the product of the lengths of one segment and its external segment equals the product of the lengths of the other segment and its external segment. So EA, the external segment, times EB, the whole thing, equals EC, the external segment, times ED, the whole thing. So the outside part times the whole thing equals the outside part times the whole thing. Okay? Also, if a secant segment and a tangent segment, so this would be a tangent segment, share an endpoint outside the circle, then the product of the lengths of the secant segment and its external segment equals the square of the length of the tangent segment. So it's very similar to this theorem. The only difference is because the tangent line, the whole thing, is the external segment, it's just the external segment times itself. So EA squared equals EC times ED. Alright, last bit. Alright, you can write the equation of any circle if you know its radius and the coordinates of its center. Okay, the standard equation of a circle with center HK and radius R is this here. And we'll do some stuff in class with this equation. And that's all for this video.